All right, hello folks. Today we're going to be talking about a problem about rotational kinetic energy. This is something we didn't have time to talk about much in class, so let's briefly really talk about it. We already know kinetic energy from Unit 1. If something is moving, like if my pen is moving, I know it has kinetic energy. It has the energy of motion. Now rotational kinetic energy, much like everything else, is very similar. If I've got this coaster right now is not moving. If I were to start rotating it, it would have energy, it would have kinetic energy because it's moving, but it's not moving in a line, it is rotating. So what we call it is rotational kinetic energy. So to make like a quick chart comparing them, if we have what we called before kinetic energy, we might want to call it now like linear. Maybe we'll call it linear kinetic energy. That we know is calculated by doing 1/2 mv squared, where m is the mass of the object and v is its linear velocity. We know it's measured in joules, J. Now, rotational kinetic energy is very similar. Rotational kinetic energy. So we're going to call it RKE, rotational kinetic energy, is equal to 1/2 I omega squared, where I, remember, is moment of inertia, and that is what we say is like how easy or how hard it is to rotate something. And omega looks like a W, it's the Greek letter omega, that is our angular velocity, or how fast something is rotating. And it is also measured in joules, because it is a measure of energy. And you'll notice, just like with a lot of our things, the linear version of kinetic energy and the rotational version are very similar. Instead of mv squared, it's I omega squared. And we already said that I, moment of inertia, is kind of like the rotational mass, and omega, angular velocity, that is like rotational velocity. So they're directly related to each other. So I'm going to walk through how to solve a sample problem of this as well. So like the sample problem, and this is from the rotational kinetic energy slideshow that was posted, is what is the rotational kinetic energy of a bicycle tire that has a mass of 645 grams, has a circumference of 2,324 millimeters, if it spins 14 times in 3 seconds. So this one, there's quite a bit of unit conversions and stuff we have to do. So the mass is given to us as 645 grams, but we've got to be able to convert that to 0.645 kilograms. We do that by dividing by 1,000 because there's 1,000 grams in a kilogram. The circumference is given to us as 2,324 millimeters, so we could change that to 2.324 meters. But here we've got to use our knowledge of circles. If we are given the circumference, we know circumference is 2 pi r. So we can divide this by 2 pi to get that the radius, not the radians, the radius is 0.37 meters. Because we're going to need that to calculate our moment of inertia. And then the angular displacement, so our delta theta is 14 rotations, and the time it does that is 3 seconds. And our unknown, we want to know rotational kinetic energy, RKE. To know that, we need to know I, moment of inertia, and omega, angular velocity. So our unknowns are the rotational kinetic energy is our real unknown, but then we also need to solve for I and omega first. So the equations we're going to use, for RKE, we're going to use RKE is 1/2 I omega squared. We're going to use I is, and now this is a bicycle, so we're going to use the hoop equation, which is just mr squared. And omega, angular velocity, is delta theta over t. So we substitute those. We don't know RKE yet, but the moment of inertia we know is going to be the mass, 0.645, the radius, 0.37 squared, and that solves out to be, in the solution I have on the answer key, I just did it all at once, but I'll do it piece by piece here in a second for you. So plug that into a calculator. And we get 0.0883. And the units of that are technically kilograms meters squared. Omega, then we have to remember if there are 14 rotations, we're going to say that is 14 times 2 pi, because there's 2 pi radians in every rotation, over 3 seconds, which is 29.3 radians per second. So now we know the moment of inertia is 0.0883 kilograms meters squared. We know the angular velocity is 29.3 radians per second. So I'm going to take both of those and plug them into the rotational kinetic energy equation. So it's going to be 1/2 0.0883 29.3 squared. And I get 37.9 joules. It's joules because it's energy. I know joules are the units of energy. They're the units of rotational kinetic energy. So that is a rotational kinetic energy problem. And it might seem like a lot, but we had to use things we knew from 5A, 5B, 5C, the ability to calculate angular velocity, the ability to calculate moment of inertia. So really this is bringing it all together, and it's relating to something we already knew, linear kinetic energy. So I hope this is helpful, and I will talk to you later.